In this lesson, we're going to study electrochemical cells. Electrochemical cells are cells with a spontaneous redox reaction occurring, meaning that the electrons are transferred spontaneously, there's no work provided, such as when we use a battery to power our calculators. There is a spontaneous redox reaction occurring. We don't need to provide heat, we don't need to provide electricity, it just happens. The electrochemical cell is an apparatus consisting of electrodes that dip into an electrolyte or an electrolytic solution, and in which a chemical reaction produces electricity or is caused by an electric current. Note that electrochemical cells can also be called galvanic cells or voltaic cells. These three terms will be used interchangeably, and they all refer to the same thing. They are a device that converts chemical energy to electrical energy. So a chemical reaction happens and therefore electricity is produced, such as the chemical reaction that happens inside of a battery. The key to this invention is to prevent the reactants in a redox reaction from coming into direct contact with each other. If they come into direct contact with one another, it's going to be instantaneous and then it's over and there's no more electricity to be produced. Electrons must flow from one reactant to the other through an external circuit, which is a circuit outside the reaction vessel. So that's why if you were to actually look inside of a battery, there's two chambers, and each chamber holds each of the reactants, so that there's something separating them so they don't come into direct contact. The flow of electrons through the external circuit is an electric current. So here is a picture of an electrochemical cell. Like I said, there's two chambers, 1, 2, and they are separated here by what's called a porous barrier to ensure that they don't come into direct contact. Each one of these strips here are our electrodes, okay, and they're dipped down into solution. That's our electrolytic solution. There is a wire that separates and it connects each one of the electrodes to each other, and that's our external circuit where a current is produced because of the flow of electrons. One particular example of an electrolytic or galvanic or voltaic cell is called the Daniell cell, and that's the one that's in the picture. Note that a Daniell cell is not an alternate word for galvanic, voltaic, or electrochemical cell, but it's a specific type. It has to include the zinc and the copper. That is the Daniell cell. One half of the cell consists of a piece of zinc placed into a zinc sulfate solution. The other half of the cell consists of copper placed in a copper 2 sulfate solution. Again, we have a porous barrier that separates them. That's this wall here so they don't come into direct contact. That's called a porous barrier, and sometimes it's called a semi-permeable membrane. And it separates the two half cells, meaning that the solutions in itself cannot come into contact with one another, but it's semi-permeable, meaning ions can go back and forth. Again, in that Daniell cell that we saw on the last page, there are pieces of metallic zinc and copper. Those are our conductors, and again, we call those electrodes. So we labeled that on the last page. But just to reiterate, that's what the electrodes are. Those are those solid pieces that we can more or less attach alligator clips to create the external circuit. The zinc sulfate and the copper 2 sulfate solutions act as electrolytes or electrolytic solutions. And electrolytes are any substances that can conduct water, electricity, as we studied in Chemistry 2202. The redox reaction that takes place in the galvanic cell when an external circuit, such as a metal wire, connects the electrodes. The oxidation half reaction occurs in one half of the cell, and the reduction half reaction occurs in the other half cell, or the oxidation half reaction occurs in one chamber, and the reduction half reaction occurs in the other chamber. So if we were to look specifically at the Daniell cell, as we saw on the last page, again we have a solid zinc electrode, and we have a solid copper electrode, in a solution of zinc 2 positive and copper 2 positive. Again, they were zinc sulfate and copper 2 sulfate, but if we were to write out the net ionic equation, the sulfate ion is actually just a spectator ion. According to their half reactions, Since zinc loses electrons, it's undergoing oxidation. Since copper gains electrons, it's undergoing reduction. When we're talking about electrochemical cells or communicating about electrochemical cells, it's kind of tedious to have to say the chamber or the half cell. So we've come up with two terms that basically just denotes oxidation in one half cell and reduction in one half cell. Whichever chamber has oxidation taking place, we call the anode. And in whatever chamber we have reduction occurring, we call the cathode. So again, these terms are just basically used so we don't have to say the chamber where oxidation takes place. We can just simply say the anode, and then we know what we're talking about. And instead of saying the chamber where reduction takes place, we can just simply say the cathode. Free electrons cannot travel through the solution. Instead, the electrons have to travel through the external circuit that connects the two electrodes. Notice from the picture on the bottom there that the electrons are flowing from the anode to the cathode. So we have the anode and the electrons are moving towards the cathode. This will always be the case, so you can memorize that. But let's explain why that is always the case. Notice that at the anode simply means where oxidation is happening. And in oxidation, electrons are lost. And you can see that by the equation down at the bottom. Since we're losing electrons, we have to draw an arrow pointing away from it to show that we're losing it, they're leaving. And in the cathode is basically where reduction is happening. And in reduction, we gain electrons. So we would draw an arrow pointing towards it, saying that's where the electrons are going. And therefore, no matter what type of electrochemical cell you have, electrons will always flow from the anode to the cathode. Because at the anode electrons are lost, this has an overall negative charge. Therefore, if I was to look at this like a battery, it would be the negative end of the battery. Likewise, the cathode will always be positively charged, and as a positive charge, it's going to attract the electrons towards it. Again, if I was to look at this like a battery, it would be the positive end of the battery. The separator between the two half cells does not need to be a porous barrier, and more often than not, it is not a porous barrier. An alternate that can be used is called a salt bridge, and that's what we're going to be using when we draw out our own electrochemical cells. A salt bridge contains an electrolyte solution that does not interfere in the reaction, meaning it's not going to actually bond or interact with any of the other ions to mess up the battery. The open end of the salt bridge are plugged with a porous material, such as glass wool, to stop the electrolyte from leaking out. So down here at the bottom, we have some sort of porous material to ensure that the salt bridge doesn't leak out into the beaker. The plugs allow ion migration to maintain electrical neutrality, meaning that the ions can go through what the actual solutions do not. This is an itemized list of how an electrochemical works. We just explained how the electrochemical works on the last slide, so you can take a few moments now to read through and reiterate how it works. Drawing out electrochemical cells can also be very tedious. And when we're trying to communicate with other people, maybe via phone, maybe through different languages, it'll be difficult to explain the electrochemical cell that you're working with. Therefore, they've come up with what's called the electrochemical cell notation. And that's just a shorthand method of explaining the anode and cathode that's in your particular electrochemical cell. We will always use the convention where the anode appears on the left and the cathode appears on the right. In the notation, the half cells are separated by double vertical lines, which represents the salt bridge. So this is the general equation for summarizing an electrochemical cell. We write what the anode is, what the electrode is, the solid piece. Then we have to do this straight line. Then what's in solution in the anode. Then we do the double line, and you should know for multiple choice purposes that that double line represents the salt bridge, or perhaps the porous barrier. Then we have whatever is in solution in the cathode, straight line whatever is in the electrode of the cathode. So we bookend by the two electrodes. See that the electrochemical cell notation has been done for the Daniell cell, and you can either include or exclude the states of matter. Sometimes we have to use inert electrodes. The zinc anode and copper cathode of the Daniell cell are metals and can act as electrical conductors. However, some redox reactions involve substances that cannot act as electrodes, such as gases or dissolved electrolytes. If the electrochemical cell does involve gases or dissolved electrolytes, there's nothing for us to clamp the alligator clips onto per se. So galvanic cells that involve such redox reactions use what's called inert electrodes. An inert electrode is an electrode made from a material that is neither the reactant nor the product, and it will not participate in the actual reaction. It's just a solid piece that's there so we can plug in or clip on the alligator clips. A very common example of this is platinum. Let's now take today's lesson and sketch and label an electrochemical cell that follows through with the given equation. The first thing that I'm going to do in blue is I'm going to draw out what a general electrochemical cell looks like. And if you remember what I draw out in blue, you can use this for any electrochemical cell question that I ask you. Then all you have to do is label it according to your particular example. So if you remember the general shape of the electrochemical cell, it would make your life a lot easier. So in 2D, we have two beakers, and these two beakers have electrodes in them, and they are dipped down into solution. They are also, leave a little space there, there's also a salt bridge that dips down into solution as well. Then these two electrodes are connected with a wire that's hooked up to a voltmeter so we can measure how much electricity is actually produced. I'm going to label this one the anode and this one the cathode, but you could do it in the reverse, it doesn't matter. Therefore, since the left-hand one is the anode, it has an overall negative charge, and the right one has an overall positive charge. That's always the same. Electrons will always flow from anode to cathode, so it doesn't matter what example I have right now, the electrons are still flowing from the anode to the cathode. In order to know how we're going to label this one, we have to break apart this given equation to the two half reactions. Mg goes to Mg2 positive, and Fe2 positive goes to Fe. We also need to include the electrons. For the first one, magnesium has an overall charge of 0, and then on the product side it's 2 positive. So I need 2 electrons here to balance that out, and in the other one I need 2 electrons there. As such, magnesium is undergoing oxidation, therefore that's the one at the anode, and Fe is undergoing reduction, so that's the one at the cathode. So I'm now going to write these half reactions in under that appropriate beaker. I've got Mg goes to Mg2 positive plus 2 electrons, and I have 2 electrons plus Fe2 positive goes to Fe. You should always write that down. So now I'm going to label this electrochemical cell using black, not really red. So at the anode, we know that we're losing electrons. We've already put that in there. We're also losing Mg2 positive ions. So we're always going to lose ions. So I'm going to label that with a blue arrow because that will always be the case. And then for this particular example, what I am losing is Mg2 positive. So I'll put that there in black. In the cathode, we are gaining electrons. So we've already put in our blue arrow saying we're gaining that. We're also gaining Fe2 positive. So I'm going to draw my arrow towards the anode, or towards the electrode, saying that I'm gaining that. And in this particular example, it's Fe2 positive that I am gaining. We also have to put something in our salt bridge, and if you had read through how the electrochemical cell works on the previous page, you would have noticed that there's an abundance of different compounds that we can use in our salt bridge. My suggestion to you is to remember one of them. That way you can always use that one no matter how many times you're asked to draw an electrochemical cell. I've always remembered and only ever used KNO3. So I'm going to write that there in blue because that's the one that I'm always going to use. Therefore, I can put the rest of it in blue as well. And the purpose of the salt bridge, if you recall, is to maintain electrical neutrality. Notice at the anode, I am gaining a positive charge. So this solution in the beaker is becoming positively charged, positively charged, positively charged. So in order for me to maintain neutrality so that this doesn't get overloaded in a positive charge, I have to send down NO3 negative. That's what's going to come down into solution there. So I can send in some negatives to counteract the positives. In the cathode, I'm losing positive, losing positive, losing positive. So this entire solution is becoming more negative, more negative, more negative. So the K positive ion is going to come down here into solution to maintain the neutrality. That's always going to be the case, so I'm going to label that as blue as well, because you can always put that in no matter what example I give you. If we were to write out the cell notation as well, this is how it would look. Remember, we start off with the electrode in the anode, and I should have labeled that as well before we moved on. So this electrode here is Mg solid, and this electrode here is Fe solid. So again, to write out the cell notation, we start off with the anode, which is Mg, straight line. What's in solution? Mg2 positive. Two straight lines to represent the salt bridge. What's in solution at the cathode, which would be Fe2 positive, straight line. What's at the electrode of the cathode, which is Fe. And this would be your electrochemical cell notation. So hopefully at this point you're understanding electrochemical cells. It is a very obscure concept, so I do suggest if you're having trouble, either rewatch the video or search for your own videos on YouTube on electrochemical cells. If you feel comfortable with this, you can now move on to the worksheet where you can practice drawing some more electrochemical cells and working some more with cell notation.